Ladies and gentlemen, may I have your attention, please? Our final parallel session is about to begin. Please take your seats. Once again, our final parallel session is about to begin. Please take your seats. Thank you.
Hello, everyone. The last talk of today's session is about Pauli Shadow Tomography. And it's a merged talk. The first part is going to be given by Robbie King. Welcome, Robbie.
Okay. Hi, everybody. Thank you for staying for the final talk of QIP 2025. The theme of this talk is how to learn Pauli observables using entangled measurements. So let's dive in. Okay, so this is a rough framework for many tasks in quantum information science. So we have some source of some interesting quantum state, and this could be, say, from an experiment, or perhaps in the future, we could receive these states from a quantum simulation algorithm inside our quantum memory, inside our quantum computer. And then we would like to read out some classical information from this state to learn about some interesting physics or predict some properties, etc. So these properties often take the form of expectation values of the state. So perhaps we have a list of observables, O1 up to OM, and we would like to learn all of their values to each to precision epsilon. Okay, so what sort of observables could we be interested in? Well, there are sort of three nice classes that we could focus on. One is local spin operators, so for example, k-local Paulis, acting on some qubits. And then a second category, which will be specifically, we'll talk about in the first portion of this talk, is local fermionic operators. So these are the ones that are relevant in, say, fermionic systems, such as electronic structure and quantum chemistry. And then a sort of third nice class of observables that you could consider is the set of all Pauli operators. And yeah, I should stress that learning the values of these fermionic operators in quantum chemistry really is something that they need to do often. For example, in these embedding methods, this is often the bottleneck is like how to read out these expectation values in a sort of sample efficient way. Okay. So, we saw this on the first slide, but just to give it a bit more formalization, this task of extracting many expectation values from a quantum state goes under the name of shadow tomography. And so this is sort of not an algorithm, it's just a sort of broad task. And yeah, it's not the same thing as classical shadows, it sometimes gets confused. So, how could we do this? So the first algorithm you could think of is to just measure each operator one at a time. So this would achieve a sample complexity of m over epsilon squared, because it's 1 over epsilon squared samples for every observable. And somewhat shockingly, in 2017, Scott Aronson realized that you could actually achieve a sample complexity which is exponentially better. So scaling only with log of the number of, log m, where m is the number of operators. But his algorithm is sort of not very practical for two big reasons. The first reason is that it's an explicitly exponential time algorithm. So the time complexity is not at all a priority for him. And the second caveat is that it requires many copy measurements. So you need to get all of your quantum states in your quantum memory at the same time and do some crazy entangled thing on all of them, which is not going to be feasible even in the medium term, where we have a sort of finite size quantum computer. So we'll see how to try and get around these two caveats in this talk. And then I guess the last motivation would be to try and really nail down the optimal sample complexity and how it relates to how much quantum memory you have, et cetera. Okay, so this motivates the definition of, in our paper, what we call triply efficient shadow tomography, which has all of these three features that you would like. You would like sample complexity, which is going like log number of observables. You would like it to be time efficient, and you would also only need to measure a few copies of the quantum state at a time. And in fact, in this talk, it will be just 2 copies will be sufficient. OK, so what are our results? Here is a sort of nice table. So it turns out that the k-local Pauli case is actually quite well solved by this classical shadows protocol. So this achieves triple efficiency in our terminology for the case of k-local Pauli operators. So that case is closed. But what we realized is if you look at the local fermionic observables, the story is very different. And in fact, you can show a lower bound that says if you only measure 1 copy of the state at a time, you actually cannot achieve this log number of observables scaling. So in fact, there's a lower bound that's like n to the k over epsilon squared. And this is the thing that really upsets a lot of quantum chemistry people, because this is a very big number for chemistry systems. And this is sort of a multiplicative factor on like how many shots of your quantum algorithm that you need to run. So on the other hand, what we find is that if you just go from single copy measurements to just 2 copy measurements, you can get this exponential improvement in the sample complexity with respect to the system size n. So we'll see how that happens. And then you can also consider a general subset of Paulis, which will be talked about by Weiyuan in the second half of the talk. And they actually have a nice characterization of exactly the sample complexity in this when you have C copies. OK, so why are 2 copy measurements so much more powerful than single copy measurements? And this is what we'll now see the reason. So what is the issue with measuring lots of different Pauli operators which don't commute with each other? Well, intuitively, it's because you cannot choose any basis which sort of simultaneously diagonalizes all of these Paulis. So that's sort of the issue you run into. But what is the insight that allows 2 copies to do so much better? The insight is that when 2 Paulis don't commute, they anti-commute, which means that if you have 2 registers and you consider the set of operators P tensor P, these actually all mutually commute with each other, because you braid the first 2 and you get a minus sign and a minus sign from the second 2. And then, for example, like X tensor X commutes with Z tensor Z. So what does that mean? That means that there is some basis on 2 registers of your n-qubit system which simultaneously diagonalizes all of these P tensor P operators. And it turns out this basis is the familiar Bell basis. So what can we do with this? Well, we could place 2 copies of our unknown quantum state rho on these 2 registers and sample in the Bell basis. And this will simultaneously give us information about all of these trace of P tensor P times rho tensor rho, which is equal to trace of P rho squared. So we can simultaneously estimate all of these. So we can square root that estimate and get an estimate of the magnitude of trace of P rho. And then all that remains is to resolve what is the sign when these are, So, the remaining task is to resolve the signs of the trace of P rho, and we only care about the ones that are large, right? That's the first thing you have to notice, right? If the magnitude of trace of P rho is less than epsilon, you can just output 0 as your estimate, and that's satisfied the task. So what remains is to estimate the signs of the Paulis that are large on your quantum state. OK, so we'll see how to do that next. And in fact, we can do this with only single copy measurements to do the second part. OK, so there's going to be 2 ways that we're going to show how to do this. I'll go through the first one, and then I'll hand over to Weiyuan after that. So this one is targeted at really this quantum chemistry motivated task of learning these local fermionic operators. And really, we would like it to be also time efficient, so we can actually try and use these eventually for the readout stage of these quantum chemistry simulations. OK. So the key insight is to build what we call the commutation graph. So this is a graph where the set of Paulis or operators that we would like to measure become vertices, and then we draw an edge between any 2 operators that anti-commute. And what you can quickly realize is that if you have a good coloring of this graph, this gives you a good measurement procedure, because a coloring is precisely a set of mutually commuting Paulis. So you can measure all of those at the same time. So if you have a coloring of this graph with chi colors, this gives a sample complexity that's linear in chi. OK. So here is the sort of proposal for how to do efficient Pauli shadow tomography. The first step is that we do this Bell sampling thing that we saw earlier. And then on all of the Paulis P that trace of P rho is small, we output 0. That's within epsilon of the true number. And then we need to measure the signs of all of the Paulis P such that trace of P rho is large. So we throw away the small ones from the graph, and we're left with a subgraph. And then what we try to do is we try to color that subgraph. And the key here is that we can expect this graph to have a good coloring. So why should we expect this graph, once we throw away the small ones, to have a good coloring? And the intuition comes from Heisenberg's uncertainty principle. So what does that say? That says that if I have anti-commuting operators, then it's impossible for a state to simultaneously be certain on those operators. So what does that mean for Pauli's? That means that you cannot be expectation value 1 on a set of anti-commuting Pauli's. So for example, one thing you could show as a sort of warm-up is that suppose you have a mutually anti-commuting set of Pauli's. The sum of the squares of their expectation values cannot exceed 1. This is sort of the familiar block sphere constraint, where like x squared plus y squared plus z squared cannot be bigger than 1. So what does this mean? This means that this graph actually cannot have big cliques, right? Because a clique is a sort of set of mutually anti-commuting Pauli's. And so you get that the biggest clique size in this graph is 1 over epsilon squared, completely independent of system size n, right? This is some constant. And you can generalize this using this Lavache theta function. And ultimately, this is what leads to us being able to show that these graphs have good colorings. So yeah, this is sort of what leads to this triply efficient shadow tomography protocol for the local fermionic operators. OK, with that, I will hand over to Weiyuan, who will talk about, yeah, I guess you'll see.
OK, thank you. It's me again. And we are going to start with an alternative approach for learning science using single copy measurement. But our approach is not computationally efficient, but it uses only single copy measurements. To start with, we again assume you have an arbitrary quantum state rho, and here is the Pauli spectrum. Each diagram is some value between -1, +1. And the first step is, again, learn the absolute values using Bell sampling. Just notice that P tensor P commute with each other, so you can simultaneously measure them and get the absolute values. And just like this. After we get the absolute values, the next step starts from an observation. So suppose we consider trace P tensor P acting on rho tensor rho prime for a different rho prime. Then the result for this trace is just trace P rho times trace P rho prime. So this means that if we know trace P rho prime, and we can estimate this product acting on rho tensor rho prime, then we can estimate trace P rho. So the problem is, how can we find this rho prime? Our strategy here is to find a rho prime with the same absolute value with rho. And we can do it classically, so we don't need to consume any more copies. But of course, this procedure is not computationally efficient. And since we can compute rho prime classically, we can also implement this P tensor P rho tensor rho prime using a single copy POVM. And the resulting answer is a signal of trace P rho times the absolute values. And absolute values, we have already learned that in the first step. So in this way, we can learn the signs using single copy measurement. And we generalize it with a theorem, which means that if you consider protocols using stronger than single copy measurement, then estimating the signs is information theoretically efficient if you already know the absolute values. Okay, next we'll enter some optimal trade-offs for estimating Pauli observables using different kind of measurements and for different subset of Pauli observables. We start with the optimal epsilon dependence. So this is actually a long-standing problem for general shadow tomography. We know that for general shadow tomography, the best known algorithm, which is proposed by Badowski and O'Donnell in 2021, they have an epsilon to the -4 dependence in accuracy, while all the lower bounds we now prove have an epsilon to the -2 dependence on epsilon. This can be quite essential in practice, because suppose you have epsilon equals to 0.001, and between this lower bound and upper bound, you can have a million time difference. And this even holds for Paulis, because when we are doing Bell sampling, we have to estimate trace p-row square. So we also need an epsilon to the -4 bound for epsilon dependence. And it's natural to ask if we can close this gap by given a better algorithm, or can we show that it is necessary? We actually show that it is necessary. We show that the sample complexity for estimating all Pauli observables using arbitrary C-copy measurement is given by this lower bound. And this lower bound contains two terms. The first term is exponential in system size, but it has an epsilon to the -2 dependence. And the second term, it has an epsilon to the -4 dependence. So we can choose this we can choose this epsilon to be smaller than 1/c. And for arbitrary c that is polynomial, we can show that protocols either have to suffer from an epsilon to the -4 scaling in epsilon for entanglement measurement, or they have to suffer from an exponential dependence on system size for unentangled measurement. So how this comes from? We actually proved it from a more general theorem for arbitrary subset of Pauli strings and arbitrary subset of C-copy measurement. So we denote the subset of Pauli strings as A and denote the subset of C-copy POVMs as M. So we show that the sample complexity for estimating Pauli observables within this subset A is characterized by this so-called delta function. It's very scary. Let's go it one by one. So this minimization is minimized over all the probability distributions over this subset A, and maximize over the measurements in the POVM set. And the final term is the chi-square divergence with respect chi-square divergence between C copies of I plus epsilon p over 2 to the n versus C copies of maximum mix. And we should note that we say characterized here means that this bound is both the lower bound and the upper bound, because we can, after we calculate the optimal pi star, the distribution, and the corresponding m star, the measurement, we can use this information to provide a strategy that gives a matching upper bound up to log factors for learning these observables. So, it's natural to wonder how this chi-square comes from. It comes from a lower bound, and this lower bound comes from a distinguishing task. So we consider distinguishing between the two cases. In the first case, you have the maximum mixed state, and the second case, you have I plus epsilon p over 2 to the n for some random p chosen from this subset A, according to the distribution pi. Suppose you can learn these observables, then you can solve this distinguishing task. We can treat any adaptive algorithm as an algorithm that has t rounds, and in each round, you perform a C-copy measurement. It is adaptive just because you can determine what to measure in this round based on previous history. And we can use a standard learning tree framework to deal with this adaptive learning algorithm. So roughly speaking, why we will have this min-max formula is because for each round, the maximal distinguishing probability for some measurement m in all the possible measurement is given by this maximal over this measurement set and this chi-square divergence between C copies of the second case versus C copies of the first case. So the last step will be choose the worst distribution pi, and by this we just add a minimum. We just add a minimum over all the pi, and this provides a min-max formula. So let's go back to the optimal epsilon dependence. Why epsilon to the -4 is necessary? We just choose A to be the full set, and choose M to be arbitrary C-copy POVM, and we choose pi to be uniform. And the chi-square divergence, you have a square. So roughly, when we are calculating this delta function, what we do is roughly to expand this C copy of I plus epsilon p and consider its square. So you will have to deal with this term. And we write it in the order of epsilon dependence. And by Cauchy-Schwarz, you can get rid of this large bracket. And the first term just gives you the 2 to the n over epsilon squared term in the lower bound, while the second term gives you 1 over epsilon to the 4th in the lower bound. And we know that our framework is quite flexible. It has many other applications, like we can show a sample memory trade-off. In particular, we consider learning Pauli observables with bounded quantum memory, just as you see in this figure. If you have a k-qubit of quantum memory, then what you do is to load a copy of rho, measure it, and store k-qubit of quantum state in the quantum memory, and then you load another new fresh copy rho, and you perform a joint measurement and load the information into quantum memory again, and you do this many times. And we note that for this kind of learning with bounded memory, the POVM element can be regarded as an MPS state with bound dimension 2 to the k between 2 copies. So by inserting this into the delta function, we can show the lower and the corresponding upper bound as this. So you can see you either have to pay 2 to the n over epsilon square, or you can make use of the quantum memory to achieve a 2 to the n minus k over epsilon to the 4. Our strategy also works for purity testing, which distinguish between maximum mixed state versus hard random state. For 2-copy measurement with n-qubit quantum memory, you can use swap test. And for single-copy measurement, you can use randomized benchmarking. And we show a trade-off here as the minimal terms in 2 to the n over 2 and 2 to the n minus k, which means that there's a transition point. If you have fewer than n over 2 qubits of quantum memory, then single-copy measurement is optimal. But if you have more than this, you can make use of the quantum memory to get something better. And we also calculate some special case for our delta function. Firstly, if you have single-copy measurement, then this delta function can be reduced to another min-max formula. And if some of you attend an earlier work from Robbie this Monday, you will know that this expression is just to measure how commuting are the p's in this subset A. And by min-max formula, you can always inverse the sequence of min-max. And in practice, if we choose some particular A, like A to be the XYZ strings, and A to be M pairwise non-commuting polystrings, or A to be like M classes of polystrings, and within each class, the polystrings are commuted with each other, we can explicitly calculate this delta. And we can also consider another case when we can only do single-copy Clifford measurement. And in this case, the sample complexity is given by the fractional coloring number of the anti-commutation graph of A. And the definition for this graph is also given by Robbie in the earlier slides. Okay, finally, we give a conclusion for our talk. For Robbie's part, we know that learning local fermionic observables with logarithm system size is impossible if you only have single copy measurement. But we also give some efficient, both time efficient and sample efficient algorithm for 2-copy measurement. That's why they call it triply efficient. And the second message is that by combining Bell sampling plus coloring or plus mimicking the state, we can provide powerful learning strategy for sample efficient algorithm for learning arbitrary subset of polystrings. And for our part, we characterize the sample complexity for learning arbitrary subset of Pauli observables and using arbitrary subset of measurements using this min-max formula. And we also, as a byproduct of our min-max formula, we also show that if you want to learn all the polystrings, you either have to suffer from this epsilon to the -4 dependence, or you have to suffer from the exponential dependence on the system size. Finally, we mentioned that our framework is quite flexible, and it can provide some results when learning with bounded quantum memory or with different problems like purity testing. And that's all for our talk. Thank you for listening.
Thank you. We have time for one question. So if you have any additional question, please take it offline. Thank you for sticking to the end of the session.